Hey, Brian Bebo here with Teledyne-API. We're in a natural setting here, basement office, so don't mind the casualness and the clutter. It's the technology and the procedures that we really want to concentrate on. So today I'm here with a Teledyne-API T700U dilution calibrator that has the ozone generator and ozone photometer option in it, and I've also got a T703U ozone calibrator, which is our level, or it's not a level, it's our transfer standard. So this is our photometer that has a ozone generator capability built inside. It has feedback control, so we can ask for an ozone target, and this will automatically dial the ozone generator in to produce that ozone target. It's got many features in the NumaView software, including programmed mode, where we can set schedule for time of day, start, duration, different phases or levels of ozone output. So this is something, and it also uses, it can use external zero air or its own internal zero air source, but it does use zero air for the reference measurement side of the measurement. So no manganese dioxide scrubber in here, so it is really a reference standard. You could certify this all the way down as good as a level 2 standard if you send it out for comparison against an SRP, standard reference photometer. A lot of folks use this as their traveling standard, so they may certify this quarterly against their level 2 standard that they keep in their lab, which could be another one of these. It could be a T700, T700U. Anyway, refer to the transfer standard guidance on all of that. But in this case, we're going to assume that this T703U here is a certified transfer standard, and so what we're going to be doing is we're going to be using the readings or the measurements that this makes to certify the photometer bench in our T700U. In my case, this T700U would be something that's residing out at an air quality station. It's something that I'm using as my on-site reference for ozone calibrations. So I may be running my nightly ozone ZSP checks from this, and also as a standard for NO2. So assuming we step through and we've got a NIST traceable calibration on our mass flow controllers, which I've covered in a previous video, and we certify this ozone photometer, we can actually use a feature in here that we call GPT preset, which essentially trains the ozone generator to run a very specific ozone target, which becomes an NO2 target when we do gas phase titration. So that's what we're going to be doing here, is really certifying the photometer in this T700U dilution system. The procedure here, for the most part, other than the screens you see, this procedure would be the same whether this was a T700 or a T700U, and really in reality this could be any transfer standard ozone photometer of any manufacturer. It could be whatever, as long as it's a certified standard and we have traceability back to either one of the NIST or the EPA standard reference photometers. But it's my preference to run the T703U. We'll get into the connections here in just a moment. I do want to step through a couple of procedures or the ways that we're going to do this. There's lots of ways to do this, lots and lots of ways. So consider this one way of doing it. Don't consider it the only way of doing it. In this case, the way, since this is essentially going to be at my ambient station and I want to certify this in its natural environment, this is going to be doing the generation, the ozone generation. So when I go through these procedures that you'll see, and I'm generating these different ozone targets, this 0 and 5 upscale ozone points, I'm going to be generating the ozone with this. I'm going to be measuring it here. It really, it doesn't matter. There's no technical reason why one or the other couldn't calibrate both or generate. Both of these instruments have the capability of generating ozone to be measured. I prefer this way. If you've got a station reference that you're certifying and that's the reference that generates ozone during your daily, your routine ZSP checks, your multi-point checks, use that guy. That's my preference again, but that's what we're going to be doing. So essentially, picture this guy. It's hooked up where it's always hooked up. It's generating this gas. It's generating it into a manifold, and that manifold is going to have our instruments that we usually test under it. So maybe our ozone and our NOx and our SOx instruments, and then I'm bringing this along, right? I've brought this into the station. Turned it on, I've let it warm up. I like to give it a good hour, sitting here making sure everything's happy after it's bounced down the road in the back of my car. I'm going to connect this thing to the same manifold, to that common manifold where the output of this instrument is going. The transfer standard is also going to measure at that point. And what I want to do is I want to minimize changes in back pressure on this instrument. So however this is operated in its normal environment, I want to leave it in that environment. And this guy, you know, ideally I would say this has probably been certified on a bench in your lab at very close to ambient conditions. You've probably got a very similar setup to this, where you've got a transfer, you know, a higher transfer standard level, and then this one being certified. But this has probably been certified with very close to ambient pressure at its photo in, and that's how I want to use it in this situation. So I'm going to assume that we've got our carb octopus or our T's, whatever we've got for our station manifold, you know, on the back wall here. I'm going to assume that that is at very close to ambient conditions. Maybe you've got that carb octopus, you've got the line going up to your glass funnel, however it is. You know, we're going to expect that that is as close to ambient. We're going to have a large enough diameter tubing going out that we can minimize back pressure, but also meet whatever our residence time requirements are, generally 20 seconds or less. So, you know, there's going to be a balance there, but that's totally your station. You know, this is, like I said, this is one scenario. So if you have really specific questions on how to perform this procedure on your specific in your specific monitoring shelter, feel free to shoot me a diagram, a schematic of your pneumatics, how your instruments are set up, flow rates, things like that. You know, I'd certainly be happy to make recommendations, you know, on connection points. Here and take a look at the back, and I've also got a little animated drawing I'll throw up too. It's a little tough to see from this, but again, you'll see the bottom instrument here is our T700U, the upper one is our T703U ozone calibrator. An important note to make is that they need to both share the same zero error source for doing this certification. So you can't really see where this is coming from, but this is a feeder line from my zero error generator. You know, we can use a T701, T701H here. It's in the other room, so we don't even really need to see that. But I've just got a T here. I'm feeding the diluent in on my T700U with the same zero error that I'm feeding the zero error in on my T703. Now the T703 here has two zero error ports, and they're pretty clearly labeled. Essentially, if you were going to utilize the internal zero air pump on this instrument, then this dry air input would be where your air would go in, and you would cap this. You would put a brass plug over this external port. In this case, since we're sharing the external air, I've got my air routed into this external air port. So that's as simple as our zero air is. Set it to 30 psi, you'll be good for those. And then I happen to have what we call our NOI special, but it's a dual output T700U here. So I've got an A and a B output. That doesn't really matter a lot, but just so you understand what's going on, in the software of this instrument, I can direct my flow either out the A or B. And this is different than our non-dual output 700 or 700Us, where you'd have a series of outputs. You'd have a couple vents, couple outputs that are all a common manifold inside. We don't have that here. So whatever you hook up here requires you to have an external vent. And it's a little tough to see what's going on here, but essentially this is that A output, and it's coming up here to my ozone calibrator to the photo in. Now I've already taken off, and if I can find it here, it's just right here. But we ship these instruments, actually both of these, with this little jumper, this little Teflon jumper that we connect between what we call photo in and photo out. So on either one of these instruments, the photometer bench, the sampling point for the photometer bench is this photo in, and the photo out is actually the output manifold. So it's the common output manifold. So when this jumper's on and I generate ozone, the photometer measures directly off the output. Of course, in this case, where and sorry if I'm going a little fast here, but where I'm going to be generating with my dilution calibrator, my T700U, I want to sample that air. I want this ozone standard, transfer standard, to sample that air. So I'm routing the output of my dilution calibrator, the instrument that I'm certifying, to the photo in on my transfer standard, the device that is our ozone standard. And so when I'm running this, I'm going to be generating some zero air out of this. It's just going to be dumping out these output ports. So we want to leave these open to the environment while we're doing this test, just to make sure we don't create back pressure on the generator and other things in here. It's a little tough to see here. I didn't have a T, but essentially I shaved a little bit of this tubing off. So this is my vent. I have just one vent only on that line. So whatever air I'm generating from my T700U that's coming up here, the T703 is going to draw that air in, any air that it needs for its sample flow rate, and all the excess is just going to vent out here. Now ideally I'd have a T. In the diagram that I'll show you in a minute, you know, I show this on a station manifold with a vent. I'm in my basement here, so forgive me, but you know, you can get the idea that that's my vent. That's essentially my ambient, you know, ambient inlet to this system. If you say it was in a real station, we're going to call this a real station, and that's the way the setup goes. So we'll go ahead back, and the rest of this presentation is going to be just some screen captures. I'm going to be running our NumaView remote for both of these instruments. It's going to be a whole lot easier to see that on the screen. So no more pictures of me after this, but we'll move on to the next. Okay, today we're going to be calibrating the photometer bench in a T700U. We'll be using a T703U as our transfer standard. In this case, we'll consider the transfer standard to be a level 2 and the T700U to be a level 3. So it's a little tough to see here on the screen, but I did want to show you the way that we're going to make these connections on the back. So one thing that's important is that we share our zero air input between the two instruments. Let's see where that is on here. Give me just a second. So here's our diluent in. So when we make this connection, we're going to have a T, and we're going to use the same zero air inlet for both instruments. So in my case, on the T703U here, you can see that I'm going to be supplying air. So I'm going to be connecting that up to the external air in. I will not be using the dry air in. That would be if we were using the internal pump, but in this case we want these two units to share the same air out, same zero air source. So then the other thing that we're going to do, we want to set this up as close to the way that it would be in a ambient shelter. So normally this output from our 700U would be going to maybe a station manifold that's going outside to the ambient air. There's going to probably be some extra ports on here that are going to other instruments. So, you know, in this case, I would tap off this instrument here, and you'll notice there's a photo in and photo out. Forgive me again, these are really small pictures here. So we've got our photo in. Normally these are going to be tied together with a little Teflon jumper. We're just going to remove that jumper for now. We're going to let the photo out, which is here, just vent to the room. So now our photo in is sampling off this common manifold, and our output of this is also going to our manifold. Now the important thing to remember is that your station may not be set up exactly like this, but what we want to try to do is make the gas that we're measuring on the T703U or the transfer standard be as close to ambient as possible. We don't want it pressurized, and we won't want to be drawing any sort of vacuum here. And then we also want just one vent in the system. So in this case, you know, you could kind of figure that these are capped off. We don't have any other instruments in this scenario. This is our vent, so when we're generating, we're going to have our excess flowing out, and that would be the way this would be set up here. So hopefully this is going to make sense to you, and we'll go ahead and proceed with the calibration. So we're continuing on here. We've already seen the physical setup of this, but hopefully on the screen here you can see everything that's going on. In the top right hand corner is the NumaView remote display for the T703U. I've got that on top, just like I physically had the instruments, so I can keep everything straight here. On the bottom right is the T700U. So again, this is my dilution calibrator. That is my station reference. It's the instrument that I will be calibrating. In the upper right is my transfer standard, my T703U ozone calibrator. That's the instrument that I'm using to assign a calibration to the dilution system. So this would be considered my EPA level X standard, either a 2 or 3, and then this would be that plus 1. So if we We're using this T703U. We had certified it against our lab standard, which had previously been certified against an EPA or NIST standard reference photometer. Then this would be a level 3, and we'd be making the station reference a level 4. But that's all covered in the EPA ozone transfer standard guidance about levels. But essentially what we're doing is we're trying to calibrate the ozone photometer in this so it has some traceability back to a standard reference photometer through these various what we call 1x6 and 6x6 certifications. Again, those are covered in the guidance, but essentially a 1x6 calibration is me going through using one of these to generate some ozone, using measuring that ozone by both units at the same time at a 0 and a 90% of the full scale, and then a series of points that are evenly distributed between that. So in my case, we're going to go ahead and assume that we're going to make this a 0 to 500 ppb range. That's actually a pretty wide range nowadays. A lot of customers or agencies are using more like 0 to 250 ppb. But just for simplicity here, I'm going to say that this instrument has a 0 to 500 ppb range. And so we're going to generate those gas points. Again, in this case, we're going to generate with our station reference, our T700U dilution calibrator. We're going to measure with both. So in this case, we're going to start with a 0 ppb. We're going to go up to a 450 ppb, which is our 90%. And then we're just going to step down through a series of points in between that. And we're going to document linearity and percent difference and all that normal stuff that we'd be covering. In the top left here is just a strip chart that I've got running. I'm using a Campbell Scientific CR6 data logger. So I'm grabbing concentration data, flow data, temperature, all kinds of cool stuff over TCP/IP or Ethernet Modbus from both of these instruments at a 1 second rate. So every second I go out, I grab that series of data from both of these instruments, I average it, I store it. In this case, I'm averaging it at a 10-second rate. That's pretty fast. Most people are going to be looking at, 1 minute and 1 hour averages, or 5 minute and 1 hour averages. I've got more of a research setup here. So for this case, I've got this set up as 10 seconds, really so that our graph can show rapid changes in ozone concentrations as we shift through these points, but not so long that we get dragged out here and have to spend all day watching this stuff happen, because that's not fun for any of us. We've got to do that in real life out in the field. So anyway, what we're going to see plotted here are 10-second averages of 1 second data for both the ozone values from, and here you can see the T703U 10-second averaging that I create. I create that 10-second averaging in my Campbell data logger, and then the T700U ozone value. So these are the readings from both photometers, and we'll be able to plot those out. Bottom left here is just a quick down and dirty Excel spreadsheet that I made up just to track this. It's not pretty, but it works. Again, I followed the ozone transfer standard guidance. I've got a few things that I would record in here. This is a work in progress, but essentially what I'm going to do on this 1x6, so again, I didn't finish that one thought, a little scattered, but the 1x6 would be this. It would be that 0, and in this case the 450 followed by 4 other points. That's considered a 1x6. So in order to certify this as a level 3 or a level 4 standard, we need to repeat this 6 days in a row. So we need 6 days of data compared back to this other level standard, which in my case is the T703U. So we would run these points, and we'd run them again tomorrow or next week. They don't have to be on concurrent days, but they need to be 6 different days against the same standard. We document, and in my case, I'm going to take 10 averages from both instruments for my 0, my span, and my other points. So I'll be recording, and you'll see it as we go. Readings, 10 10-second readings that we'll record in here. We'll get our average. We're going to get what I'm putting in here as a corrected average, right? Because assuming this is a level 3 standard, it's got a slope and intercept that came from its comparison to a level 2. That whoever certified this back in the lab, they compared it to that level 2, which was previously compared to an SRP. They found the comparison. It had to have passed if I'm using it here. And there's a slope and an intercept associated with it. And that's going to be on the certification sheet that, you know, your lab or maybe you have somebody, a third party certified, they're going to give you those values. In my case here, I'm going to set these to 1 and 0. I've got them on my form here. But what's happening is these are the values I'm going to be entering from my DAS, which we'll see up here. So this is just what really is the raw average for the level 2. Now over here, I correct that value. So I'm just taking the value, subtracting the intercept, dividing by the slope. Standard correction factor, right? So it's looking back to column H there, which is this guy. So it's just a way for me to make sure that I've done that that certification or that correction factor. So again, raw values, raw averages here. But this average, this is going to be called my corrected average. This average is going to be the average of this column of data, which is corrected back. So that's this average here. I can share this spreadsheet with anybody that wants to see it. It's probably got errors in it, but it should be pretty close. Then we've got our absolute percent difference and our absolute PPB difference in these columns of the corrected average compared to the displayed here. So we're going to step through. We're going to start out here. Now, an important thing to remember that we want to cover on the device at the site is under this diagnostics menu. I did that a little quick, so let's go back. Utilities, diagnostics. We've got this thing called back pressure compensation. And what this does in our ozone analyzers, it's a single tube photometer bench. So we go back and forth between reference gas and sample gas. You can read about that in the manuals for sure. I'll give you a quick synopsis of it. Essentially, in an ozone transfer standard, which is what both of these instruments are, the reference measurement, that I naught, if you call it that, it's measured using zero air, not zero air that's scrubbed from sample air, but actual zero air from a zero air generator. Ozone free, SO2 free, whatever free, zero air. So we take one cycle, we flush that glass tube out with zero air, and we measure the loss of intensity from the ultraviolet light to the detector through that bench. That's our reference measurement. Now we fill it with sample gas, the gas that we're generating in this case. We never want to have ambient air inside of a ozone transfer standard. That's just sort of faux pas. We don't do it. So when I say sample gas, I really mean the gas we're generating. So we did our reference measurement with zero air. Now we fill it with the gas that is being generated by whichever instrument's generating it. But it's a sample gas, but it's really calibration gas, if you'd say. What happens here is that zero air measurement inside of any one of these instruments, we have a vent. So we're supplying zero air to the reference side of the sample reference solenoid, and then we're venting whatever excess there is there, so that really the reference measurement is made as close to ambient pressure as possible. There may be a tiny bit of back pressure because we have excess air there, but really you can consider there's no back pressure on the photometer bench during that reference measurement. It's at ambient conditions. Now, when we switch to that sample, we don't guarantee that because we're generating what? Maybe we're generating, in my case, I'm going to do 5 liters of air. So we've got 5 liters of dilution air being generated. It's pumping out the back. The sample measurement in that photometer bench is going to use some of that. It's maybe 500, 800 cc's. The rest of that, 4+ liters per minute, is going out the back. Where is it going out the back? It could be venting right out of the bulkhead, but in most cases it's going to be hooked to some tubing, and it's going to be going to a manifold, maybe up to your inlet if you're doing a through the probe type cal. There's going to be pressure there, and that pressure is going to be different than the reference. So this back pressure compensation compensates for that. It's a software feature that compares the pressure from the reference and the measurement sides, and it comes up with a calibration factor, a correction factor for that. It's very important, and you can read about this in the manual. You want to do this on site. You want to do this hooked up in the configuration that this calibrator is going to be used. So if you've got 8 feet of 1/4 inch thin wall tubing coming out of the back and going into a manifold, and that's going to some instruments, and then it's going up to your ambient inlet, and that's your vent. You want to make sure that it's all hooked up. All those analyzers are just the way they're going to be. Run this back pressure. I'm going to go ahead and calibrate it now. We're going to say yes. So what it's going to do is it's going to turn on 5 liters of air, in this case, it's going to generate that 5 liters of air, pushing it out the back, and it's just going to start making a measurement. So the photometer's on in this thing that's generating 5 liters of air. It's measuring with the back pressures that it's going to have in real life, and it's going to step through and do this back pressure computation and come up with a factor. I'm going to go ahead and pause here while this runs. Actually, we'll just let this run through, and I will mute myself. We'll speed this up in the post video. Okay, so we've run that. You can see we've got, I didn't record what this was before. Generally I would, but we can look back through the video. But we're pretty close to where we were before. So we've set the back pressure compensation. I want to do this before I certify this instrument. And while it's in its sort of natural environment, I keep saying, but where it's set up. So now what we're going to do is we're going to calibrate the photometer in the T700U. That's going to be under bench cal here, and so this is going to set the initial 0 in span for this instrument. Now once we've done this, we're going to step through our 1x6, and then the six 1x6s or 6x6. We're going to change this again. Changing this would sort of negate the 6x6, and we'd have to go and start back over. And the idea is with that 6x6 is, over time, during this initial certification, we do this over 6 days. It'd probably take us 2 weeks in real life because we don't work on weekends and such. But then, once we've got the initial 6x6, maybe every quarter, maybe every 6 months, beginning and end of ozone season, depending on how your organization does it, we're going to do another 1x6. And so when we do that next 1x6, down the road, we're going to toss out the oldest 1x6 and add in the newest 1x6. So we've always got 6 days worth of 1x6s averaged in that are giving us our calibration, our certification, our reference back to the SRP in some distance of time. But ideally we're never going to have to really calibrate this. The ozone photometers don't tend to drift. These calibrations stay good for a long time, and the correction factors that we're going to generate through this 6x6 are going to compensate for small amounts of drift here. So in our T700U software under this bench cal, remember we were under utilities, diagnostics, bench cal. We've got 2 different options here. We've got 0 span and X0 X span. So the 0 span tell the instrument when I press one of these that I am going to be using this instrument to generate the air. So when I press 0, the T700U, this one that I'm operating here, it's going to turn on 0 air at 5 liters per minute. It's going to push it out the back. And I should come back and say the reason it's going to do it at 5 is that in my VARs, there's a VARs called target flow, and I've got it set to 5 liters per minute. That's the value that this uses for dilution. For dilution on the bench cal. So when I press 0, it's going to turn on the 0 air generator at 0, obviously at 5 liters per minute, and we'll calibrate there. Same thing with span. It's going to turn on whatever target value I've got in here when we get to that point, and we'll calibrate. Now if I used X0 and X span, that's telling it that, hey, actually we're going to be using the photo in, essentially. Something else out there in the world is going to generate some ozone and some 0 air, and we're going to use those values, and we're going to tell the instrument what that external value is, and it's going to set its photometer to its slope and its offset to those. So let's go ahead and get started here with the 0. You can hear the pump kick on in the background. We should start seeing a reading up here, and because we got to compare this to something, we're calibrating, right? We need a reference value. So on my T703U here, my transfer standard, remember that we had that photo out disconnected. It's just venting into the room. Now in order to turn this instrument on, in order to get it to read ozone, I've got to still go into the generate menu here. I'm going to generate 0 ppb of ozone and hit generate. So you can hear that second pump start up. What that does, the generate turns the photometer on. I'm measuring the photo in of my transfer standard is hooked to the output of my device under test here. So now, while I'm generating 0 with my station dilution monitor, my T700U, I'm measuring it up here with my transfer standard. These values are what I'm going to compare to. Now if there's a correction factor on my sheet, that would work it out. I wouldn't compare it directly to this value, I'd compare it to the corrected value. So that may be a little bit off by a few tenths, maybe even a ppb. In this case, we're going to assume that it's a perfect world. The correction factors are 1 and 0. That'll make things simple. I've got those entered in here as 1 and 0. So this corrected column and the raw column for my level 2 are going to be the same values. And of course for 0, I'm not going to really match these up. If this one comes in at, you know, minus 0.5 or minus 0.8, you know, I'm going to assume that this is 0. I'm just going to calibrate this guy to 0. It doesn't really give me an option to put a value in here because 0 is 0. So we're going to let these run. You can see that I've got data coming in here now. Both the photometers were turned on, so that's good. We can be looking at a couple things here. We could look at stability for these generations. Now, let me step back too. Remember, I'm a scatterbrain. If I jump out of this screen, it'll stop this calibration. So it's really important not to leave this screen while I'm calibrating. So if you wanted to see your ozone stability factor from this, you'd need to be capturing it on an external data logger. I'm going to use the strip chart as a representation of that. I think I might have stability captured in here. Let's take a look. T700U. See, I don't think I have stability in there. Nope. So we can't really look at that stability factor here. But we can see it on this guy up here. If we go into our O3 stability, that's going to be a good indication that we're stable, that the instruments had enough time to stabilize to this 0. You know, good practice is going to be 10 minutes, 15 minutes for this, especially for this initial 0. But really, we want to see that stability close to 0. We want to see these numbers not changing. And when we get to that point, if needed, we can adjust the 0 on this. You can see right now that I'm coming in at minus 0.3. You know, I probably wouldn't bother to adjust this, but in this case, since we're certifying the instrument, we're trying to get it as close to perfect for this initial time, since we know we're not going to calibrate this again for a very long time, we hope. You know, certainly we want to get it as close as we can. So we'll just watch this for a moment. So like I said, we have this O3 stability factor. You know, we can also graph the values here on our front panel by clicking on the concentration. It's going to also give us a good indication that we're stable. This looks pretty dramatic here, but if you look at the y-axis, you know, we're 0 to 1.5 ppb as we started this up, so we're really not that dramatic at all. But we do want to see that flatten out a little bit. It's a little tough on my scaling here with the 0 to 500. We could edit that a little bit for now, just to make it a little bit better of a value to see. There we've got some movement there. We could even zoom it in a little bit more, since this is really our 0. That's the nice thing about using these Campbell data loggers is graphing and data collection are just very flexible. For doing stuff in a lab, I really prefer this method here. Something that you can, and even a transfer standard. If you've got a way to, you know, it can be tough with some of the commercial DASs out there, but if you've got a way to connect your transfer standard up to your DAS while you're on site, even if it's just an analog line that you sort of keep hanging there and you plug it in, you know, do a quick analog output cal on it when you plug it in, but you know, some way that you can actually trace this and track it. It's really nice. It's good for you know, leaving a paper trail and showing what your values were. You know, using Modbus, you could even bring your own Campbell data logger with you. There's no reason that multiple data loggers can't pull, say, this T700U at a station. So maybe I've got an NVDAS or an ESC or a Campbell data logger out at that site collecting data over Ethernet Modbus. I bring in another Campbell CR6, I plug it in, it's got its own IP address, and it's got, you know, the IP addresses of those instruments I'm testing, and you could have this exact setup. You could have a secondary QA QC data logger that you bring to the site. You know, I'm not saying that's the right way to do it, it's an option, but if you have the ability to capture your transfer standard data, you know, for comparison, it's really handy. I do like leaving a paper trail when somebody tells me I was rushing or whatever they want to say. Like, I've got this data I can plop out here and say, no, you can see it was flat here, it was stable, I waited long enough. And they say, good job, Brian, go get a beer. And everybody's happy, so there you go. That's my advice for the moment. So we'll just watch this. It's like watching paint dry. Listening to those pumps. Those are pretty quiet pumps compared to others. I'm just going to be quiet here for a minute. You don't need to hear me talking the whole time. So. You'll notice the numbers not matching up perfect here. We got minus 1.6 and minus 1.7. Remember, this is a 10-second running average of this instrument's data here, so they'll be off by just a touch depending on the noise of that measurement. We're just going to let this one run. Since it's our initial zero, these things have just been fired up. You know, this initial zero is important. Once this one's stabilized, it's going to, we should get a faster response every time we switch around here between different points, since we've sort of got the instruments, they're stabilized to this calibration air, this calibration gas that we're providing. So, you know, we're coming up on, say, 12 minutes here since we started this. We'll look to get that little cycling out. Remember, we are looking at you know, -5 to +5 scale on our strip chart here, so we'll expect a little bit of variation. Okay, I'm going to call it. I'm going to say good. We're almost 15 minutes in. You know, in real life I'd go a little longer than this even, and I'd look for this, you know, a little bit more of this where they're real close together and tracking. But in the interest of expediting this video, I want to show you the procedure here. So you can see we're really pretty good. Our T700U, which is what we would be adjusting here, is -0.3, -0.2. But we'll go ahead and make this adjustment anyway. We'll hit this calibrate. Yes, do you want? Boom, we're going to be reading 0 now. So it just really kind of sweetens it up a little bit here. We can watch that for a little bit of time if we want, but we're essentially 0. So now we can go ahead and go to our span. Again, assuming that we are looking at a range of 500 ppb here, and we want to make this adjustment at 90% of that scale, we're looking at 450 as our target. We can see what our measured is here. This is the response, or the reading, the current reading from the photometer in this T700U. Obviously we've got the readings up here for this instrument. We'll reset our scale here so we can see that. Let's bring that back up to 500 for our y-axis scaling. We may overshoot a little bit. Remember, these have feedback in them. The T700U on the bottom here is generating that ozone, so it's going to turn on the lamp and start dialing that in based off its own feedback, what the photometer is telling it is happening. So it starts out, might shoot a little high, it dials the current to that ozone generator lamp down, down, down until we get to that 450 target, and then it sort of locks in there. So we're going to wait, again, a little bit of time for that to stabilize. It'll be probably 5 to 10 minutes here, but in the real world we'd want to wait. You may have a fixed amount of time in your guidance, your QAPP crap that tells you how long you need to wait. If not, really look for stability, look for a flat line. So we're going to watch that. standard that we're comparing to. So we've got 451.4, we hit calibrate, yes, and we make these two equal each other. Now, because our target here is 450 and we've just told it it's 451, there is going to be a little bit of time that it's going to drop down. But essentially we've calibrated this instrument. We're going to go now to the point where we want to start documenting these in here. So we're going to start out with our 0. So here we're going to go to generate, auto, and we want to make sure, let me show you the difference here. We don't want to hit, we don't want to press 0 here. If we were to generate a 0, then the photometer isn't on. We're generating 0 error, but we're telling the T700U not to use its photometer. So it's important when we're generating a 0 to actually turn it on and ask for ozone at 0 concentration. And I'm going to run it at 5 liters flow. That's what I use to calibrate at. That's what I use for my back pressure compensation. So that's where I'm going to run these points. Essentially, I'm calibrating this T700 at 5 liters per minute. Now you can use it outside of that range depending on back pressure and other factors, but that's going to be its sweet spot. I can document that all of these adjustments and checks were done at this flow rate. It's going to be really happy here. Now that we're generating using the auto mode, we can go back out to our home screen. I'm going to go ahead and step away to get a drink of water, and I'm going to set my timer here. This is what I'll often do if I'm out at an air quality site or whatnot, is try to multitask a little bit. So I'm going to go ahead and set my timer here for 10 minutes, and I'll be right back. I'm going to mute this while we're waiting for things to stabilize. Alright, so we got 10 minutes in there. We're going to go ahead and take some readings here. So again, we're going to be using the DAS readings. That's usually the correct way of doing this. If we've got a DAS, we want, our sort of our data of record values here. And so I'm just going to enter the values I see up there, minus 0.6 and minus 0.9, and then minus 0.7 and minus 0.7. minus 0.8, minus 0.8, like again minus 0.8, it's like it's staying pretty steady there, minus 0.9, minus 0.6. Remember, since we're getting 10 readings here, if we skip one or whatnot, it's not the end of the world. We just want to get 10 simultaneous readings, and as close to direct succession as possible here. It's like it's minus 1 and minus 0.5 again. Minus 1 and minus 0.7. When it's real stable, it can be a little tough to tell when they've actually changed on us. So we could have a timer or something. Well, we should be updating every 10 seconds or so here. Alright, minus 1, minus 1. So that's our 0 right there. And we're going to go ahead and switch this into our 90% point. Hit generate. You'll see it's going to dial itself in there, and we'll go ahead and set our timer and be back in 10 minutes. Alright, another 10 minutes of life has gone by here. We're back, and let's roll through some numbers. Just a second to update there. 448.6, 449.2. Alright, so that's our next row. We're less than 1 ppb difference between them and 0.2% absolute difference between them, so looking good. You can see these fields I have just set up as percentages. So up here where I put my analyzer range in, these are just, you can see 90%, 60%, 30%, 20%, and 10%. So that's where these targets are coming from. And that way you can see I can put in any range here I want, and sort of does the math for me. I've arbitrarily picked those values. You can set it however you want. But our next target here would be 300, so we're going to go into the generate. We'll change this to 300 here, and generate. And again, we'll give it a little bit of time, and we'll be back. Alright, looks like we're pretty stabilized here at our 300 point, and record our averages, 300.6, 300. Okay, now on to our next point here. Okay, we're back at it here. Enter these values. Oh, I missed one up there, didn't I? I'll just start over here. 149.3, 149.3. Okay, save that, make sure we don't lose it. We'll go down to our second to last point here and set our timer. Okay, nothing here. Okay, and last point here. Alright, final points here. We'll wrap this up. Alright, so we got all our points. Let's go ahead and put these guys both in standby. Remember, we don't want to sample any air off those, so those are both in standby. Let's grab this and make it a little bigger so we can see what's going on here. So we've got all our table in here, all our points. Remember, no correction factor. Let's just take a look and see what would happen if there was a tiny correction factor. Let's say that was 1.015, might be a typical one, and minus like 0.8 ppb offset. You know, that actually threw the percent difference here off a touch. with that correction factor. So you can see how the display could be affected. That's why we want to factor that in. We don't want to find out after the fact that that correction factor put us in or out of adjustment. But since we made our adjustments to these factors, that's why that point went out a little bit as I changed those, because I was essentially comparing it to an uncalibrated instrument at that point, if that makes sense. But so we've got our corrected averages across here, our comparisons. We've got our slope and intercept comparing our x-axis here is the level 2, our y-axis here would be the level 3 for each set of points, and that's what we end up with. And so these are what we would use to compare. We would end up with a set of slope and intercepts for each of the 6 days or 6 runs, and we would average those together at the end. Again, following guidance. Always make sure you refer back to that guidance. So hopefully that gives you an idea of what we've done to calibrate our T700 photometer, or T700U in this case, calibrate it, and then do our comparison against our transfer standard analyzer.